Hello, I'm Mike Ackerman, and I'm delighted to spend the next few minutes together as we think about understanding the cardiac action potentials of the human heart and the relationship to excitation, contraction, coupling for the boards. So we'll keep this very focused, as we do so, I'm a conflicted individual. These are the conflicts of interest that I share with you. I don't think they matter to this, but you can be the judge of that. More important to disclose is what we're going to do together over these next 20 to 30 minutes, and that is first, we will work to recognize the basic architecture for and regulation of the ion channels in the heart. We'll then assemble, compare, and contrast the action potentials of the nodal cells, the SA node and the AV node, and then the working myocardial cells of the atrial cardiomyocytes and the ventricular cardiomyocytes. And then we'll integrate this cellular excitation with contraction coupling. So ultimately what I'm hoping to do is that you will understand the basic principles of the ion channels of the heart and how they orchestrate in order to create the various action potentials in the various tissue types within the heart cell, and then how this coordinated, orchestrated action potential propagation enables calcium entry to mediate excitation, contraction, coupling. The ion channels are like, as my mentor once said, a donut in the middle of a football field. This is a crystal structure of one such ion channel, and we need to work to understand the physiology of these channels. There are the pore-forming alpha subunit, like the channel that I showed you, and mutations in this pore-forming alpha subunit, like the sodium channel alpha subunit encoded by SCN5A, mutations cause disease. They cause several different heart rhythm diseases. Gain of functions cause to underlie type 3 long QT syndrome, while loss of function mutations in this alpha subunit underlies about 25% of Brugada syndrome. But these pore-forming alpha subunits are not alone. These ion channels are complex structures with several different auxiliary proteins, channel interacting proteins, chips, that modulate, refine, adjust, fine-tune the behavior of these ion channels. But what do these ion channels do anyway? How are they controlled? So here, for a voltage-gated potassium channel, you and I are going to learn and realize that these channels have built-in voltage sensors, those positive amino acids indicated there, that sense the changes in membrane potential. And in response to membrane depolarization, the voltage sensors physically move in the membrane. That movement causes the so-called S5, S6 pore region to open, and that opening allows the egress, in this case of potassium channels, of potassium ions down their concentration gradient from inside the cell to out the cell, and that movement of potassium ions generates current measured on the order of picoamps, and that movement of potassium ions out the cell then starts to drive the membrane potential back, repolarizing it back to the resting membrane potential of the heart. That's what potassium channels do. And each channel has its signature thing that it does. And so for us to understand that, let's start with a completely blank slate. In order to understand what ion channels do, because after all, these are passive proteins that simply, when they open and close, they allow the movement of the ions that they were designed to allow passage to move down their electrochemical gradient without the need of energy. Well, how did they move in the first place? It's because of gradients. That's because of the pumps. So we have different concentrations of ions. Calcium, different on the outside versus inside. Sodium, more on the outside than the inside. Potassium, higher levels of potassium on the inside than the outside because of the pumps. And that gives rise to so-called membrane potentials, or the Nernst equilibrium potentials. And we know that, for example, if all there was the difference in concentration of a specific ionic species, say for example potassium, and we put that in the equation, then we would see that the reversal potential for potassium is minus 98 millivolts. In other words, any time a potassium channel opens that's selective for potassium, its job, what it's trying to do, is to get the membrane potential of that cell back to EK, back to minus 98. And it allows the efflux of potassium down the concentration gradient from in to out in an effort to, and as a result, moving the membrane potential towards EK. But that's not what calcium channels do. Calcium channels, when they open, permit the influx of calcium down its concentration gradient from out to in, and in doing so, it's trying to depolarize the membrane potential to plus 150. Sodium channels to plus 70. And if you know those three things, the reversal potential of potassium selective species, a sodium selective species, a calcium, you can actually picture and begin to construct what the action potential must be emanating from. And we see that here with membrane potential on the y-axis and time on the x-axis, and you see the configuration of a nodal cell action potential and that of a ventricular myocyte action potential. And immediately some things are called to your attention. The resting membrane potential in the ventricular myocyte is more negative than it is in the nodal cell. So there must be more potassium channel forces open at rest for it to be driven closer to EK. You also see that the upstrokes are different for the nodal cells and compared to the ventricular myocyte, and we'll see that there is a different depolarizing force that's responsible for the nodal upstroke compared to the myocyte upstroke. And we'll come back to that as we build this together. So to review, when a calcium channel opens, there will, in physiologic terms, always be the influx of calcium from out to in, and that movement of calcium will cause a depolarizing effect trying to move the membrane potential. If left unopposed, it would ding, 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 ding to plus 150. Sodium channel, same thing. Always depolarizing, always influx of sodium, and that movement of sodium from out to in would have a depolarizing force trying to get the membrane potential to plus 70 if left unopposed. On the other hand, potassium channels, movement of potassium ions from inside the cell to out, that is an efflux of potassium ions, and that efflux causes the membrane potential to try to get towards EK, that is minus 98. You know those three things, you're good to go. Now, these ion channels are controlled by many different things. They're gated. What controls the opening and closing of the channel is affected by voltage, by time. They're modulated by different things. Most phosphorylated ion channels work better when they have been phosphorylated, for example. Now, let's take those basic principles and construct the nodal cells first, that is, of the SA node, and we'll eventually do the atrial myocyte as well in just a few minutes. And for simplicity, we'll think of the SA node and the AV node together, and we'll show what makes a ventricular myocyte different from the atrial myocyte. But let's start with the ion channels that underlie, that construct the nodal action potential. Now, of course, when we think of, in cardiology, our pharmacology of the nodal agents for rate control, we think of adenosine, beta blockers, calcium channel blockers, and digoxin. I'll just have a couple of pearls, if you will, on adenosine. But here's the nodal action potential. It is less negative than the myocyte one. Why is that? Well, besides a potassium channel force, there's a so-called funny current, which is more of a depolarizing current, and the presence of the IF moves the membrane potential away from EK. So its resting membrane potential is set different. It's set in a region that enables automaticity. Then you see that the upstroke is dependent on the depolarizing force that comes from L-type calcium channels. That's why calcium channel blockers have a negative chronotropic effect. They slow down the nodal upstroke. We'll also see that calcium channel blockers have a negative inotropic effect because of the effect on the calcium channels in the working ventricular myocyte. And the nodal cells have a population of potassium channels that is minimally present in the cardiac myocytes. In fact, we exploit this population of potassium channels every time we try to terminate an SVT. So whether we try to break the SVT by doing a carotid sinus massage and activating cranial nerve 10 to release acetylcholine from the vagus nerve, or we pharmacologically give adenosine fast, what we're doing is we are targeting at the cellular level, trying to recruit a population of potassium channels and turn on that population of potassium channels, thereby providing a force that tries to drive the cell membrane potential more negative. And in doing that, make it take longer for the next upstroke. So for the boards, that's what SVT maneuvers are doing. That's what the vagatonic maneuvers are doing when we turn on the vagus nerve, release acetylcholine, the neurotransmitter, or whether we're using adenosine pharmacologically, they are binding to their respective receptors, acetylcholine to the M2 muscarinic receptor, adenosine to the purinergic receptor. That binding to its G protein coupled receptor then activates the G protein subunit, the alpha subunit and the beta gamma subunit, and it is the beta gamma subunit that binds to and turns on that population of otherwise quiescent potassium channels, the so-called IKACH potassium channels. Potassium channels get turned on. What happens? More efflux of potassium ions. What happens? Membrane potential heads more negative towards EK, and that slows the system down. And if the AV node is involved in that reentry circuit, then it will be broken with these maneuvers that are designed ultimately to turn on IKACH. Well, let's now turn our attention away from the nodal action potentials and nodal pharmacology to the action potentials of the atrial muscle and the ventricular muscle. From a pharmacologic perspective, for the boards, we need to just remember that we have the rhythm control drugs that are the class 1s, the sodium channel blockers, and we'll show where they exert their effect, and the class 3s, the potassium channel blockers. So let's build the action potential of the working myocyte. First, we see that at phase 4, the membrane potential, the resting potential is around minus 86 millivolts, and immediately you would shout out potassium channels. There must be more potassium channels open in abundance than anything else, because that's the only thing that can get the membrane potential that close to EK. And in fact, that resting membrane potential can be influenced by things that disrupt potassium, like hyperkalemia. So hyperkalemia would change that Nernst equation, would cause the EK to become more positive, less negative, right, to move up north, and that can alter the excitability of that tissue. But let's not deal with things like hyperkalemia. Let's come back to, we're at phase 4. Mostly potassium channels are open. That population of potassium channels is IK1. And then all of a sudden, bam, we go into a rapid upstroke in the ventricular myocyte at phase 0 because of the activation of the sodium channels, trying to move that membrane potential to plus 70 millivolts, doesn't quite get there, tops out at about plus 10 millivolts, sodium channel activation. What do the class 1s do? The sodium channel blockers, they slow the upstroke velocity. So that's phase 0. Then it didn't reach plus 70 because there was an opposing force. That opposing force didn't let it hit plus 70 and starts pulling it back. That is a population of potassium channels called ITO. Then we enter into the plateau phase where there's a balance now between the inward depolarizing force, the L-type calcium channels, and several different populations of repolarizing potassium channel forces. And the balancing act between an inward calcium channel force trying to get it to plus 150 and the repolarizing, hyperpolarizing potassium channel forces trying to get it to minus 98 leaves it at this plateau for a period of time until the calcium channels close and the potassium channels stay open and continue to drive it towards EK during the phase 3 repolarization. It's brought all the way back down to rest. It's in phase 3 by the presence of IKS and IKR potassium channels, and then driven all the way back to rest and held there until the next excitation, until the next activation of the sodium channels, again at phase 4 by the presence of IK1. Now let's take a look. What if we add an extra repolarizing force at phase 3, another distinct population of potassium channels, and let's call it IKUR? What would happen to the action potential duration? Well, that would cause the plateau period to shorten, to cause repolarization to occur more quickly, and in fact, what you and I have just done is convert the ventricular myocyte into an atrial myocyte. The atria has much more abundance of IKUR than the ventricle does, and that's why its configuration has a shorter plateau period, a faster phase 3 repolarization because of the presence of an extra repolarizing force, an extra potassium channel population. But let's go back to the ventricle, and now let's take one of the principal potassium channel phase 3 currents, the IKR, and remove it, either because we pharmacologically inhibited it, called many of our class 3s, right? Or also called drug-induced QT prolongation, or we genetically damaged it with loss of function mutations, called type 2 long QT syndrome. Either way, the removal, the lack of IKR, has the effect of prolonging the action potential duration, making the plateau phase longer, making the refractory period longer, and for the class 3 drugs, that's exactly what the intended purpose is, to prolong the refractory period, to hopefully have better rhythm control. But as we know from the experience of long QT syndrome, both genetic and drug-induced, that it's only up to a point, and then you start experiencing the other edge of the double-edged sword. And so that's IKR block. And now let's come back to the ventricular myocyte. We have IKR present as well, but now we rev up IKS. Well, how do we rev it up? Run from the lion, tigers, and bears, oh my. Sympathetic stimulation. We're going to get excited. We're going to phosphorylate that channel. That channel in a sympathetically stimulated pKa phosphorylated state works better. It's a better phase 3 repolarizer. What happens? We shorten the action potential. It's a good thing to do to shorten your ventricular action potential when the heart is being asked to run faster and faster. And at the same time, we need to bring in as much, if not more, calcium, which we're able to do by the pKa phosphorylation of the calcium channels and so forth. Now, these are the main targets for the class 1s. The sodium channel blockers are acting at phase 0. The calcium channel blockers, the L-type principally in the heart, diltiazem and verapamil, acting in the plateau period. And when you block the calcium channels, in the nodal cells, you slow the upstroke, negative chronotropic effect. In the working myocytes, you shorten the action potential duration, create less time for calcium entry, negative inotropic effect. And the class 3, the class 3 drugs act at phase 3 and virtually act only on IKR potassium channel. That's dofetilide, that's sotalol, and of course amiodarone is not only an IKR blocker, it's a mixed channel blocker. It affects many different channels. And importantly, virtually every drug that has an unwanted QT prolonging side effect exerts that effect by blocking IKR. Well, what have we done here? We've created the nodal action potential, the atrial muscle, and we showed that the atrial muscle is the atrial muscle because of the presence of IKUR. We have the AV nodal action potential, which if we turn on a new population of ion channels, the IKACH, the potassium channel, that can break SVT circuits. So we target IKACH, we activate IKACH with adenosine, with vagatonic maneuvers. And we built together the ventricular muscle action potential. We talked about the resting phase 4 being closer to EK because almost only potassium channels are open. Rapid upstroke vis-a-vis sodium channel activation compared to the calcium in the nodal cells. Doesn't quite hit the sodium reversal potential of plus 170 because it's pulled down by the simultaneous or the near simultaneous activation of various populations of potassium channels. The plateau period with a balancing act of the inward depolarizing calcium channels and the outward repolarizing potassium channels until the potassium channels win the day, drive it back to EK at phase 3 and being held at the resting membrane potential near potassium's reversal potential again by IK1. We talked about the importance of IKR as the target of all of the class 3 drugs, but also the target of virtually every drug, antibiotic, antipsychotics, and everything in between that exerts an unwanted QT prolonging side effect with the potential for drug-induced sudden cardiac arrest. And in the end, what is that plateau period that's doing that's having the calcium entry through the L-type calcium channel? Well, it couples that entry of calcium, then finds and binds to the so-called calcium release channels sitting on the sarcoplasmic reticulum that is responsible for unleashing the kraken, if you will, the storehouse of a tremendous amount of intracellular calcium confined in the sarcoplasmic reticulum. And those calcium release channels are also called the ryanodine receptors. The calcium that comes through the L-type calcium channel binds to the ryanodine receptors. That opens, activates the ryanodine receptors so the intracellular warehouse of calcium can come out of the SR in systole, right? Find the troponin C complex on the sarcomere and then mediate the excitation, contraction of the sarcomeric apparatus by the binding of calcium to troponin C. Then that calcium needs to be quickly taken up back into the SR through the Circa pumps, extruded out of the cell through the sodium-calcium exchanger so that the diastolic levels of calcium are reduced quickly and dramatically. So let's see how we did as we think about the basic components of the action potential, the ion channels, their regulation, the principal job of a potassium channel, drive to EK, the principal job of a sodium channel, influxing, depolarizing, trying to get to ENA, plus 70 millivolts, the principal job of a calcium channel, depolarizing through the influx of calcium ions, trying to get to the reversal potential of calcium. This is all, what is that reversal potential? That's set up by the pumps. And with this in mind and those component parts together, we then built, as shown here, the ventricular myocyte action potential. You also helped me build the atrial myocyte, and we discovered that with the way we convert the ventricular myocyte into an atrial myocyte is to add another potassium channel species in phase 3, the IKUR channel. Let's see how we did. These are most likely to be the 3 or 4 most likely boards questions related to action potential physiology. So you read that the cell's resting memory potential is minus 80 millivolts. The predominant ion channels that must be open at this time are what? Sodium channels, potassium channels, chloride channels, and calcium channels. And you would quickly shout out potassium channels because that's the only thing, population of species, that can drive that negative, getting it close to EK. And that is what is responsible for the resting membrane potential of the cardiomyocytes. Number 2, drug X blocks phase 3 repolarizing potassium channels in excitable tissues like the heart. Drug X's primary mechanism of action is to 1, accelerate repolarization and shorten the action potential. 2, decrease conduction velocity. 3, slow down repolarization and prolong the action potential. Or 4, decrease calcium entry during the plateau period. So drug X would also be called a class 3 antiarrhythmic agent because that's the mechanism of action of class 3s, is to block the phase 3 potassium channels. And when you block a phase 3 potassium channel, you slow down repolarization. It takes longer to drive back to EK. You lengthen the action potential. You lengthen the refractory period, which for class 3s, that's the intended mechanism of action as it's antiarrhythmic. But as we talked about, you can have unwanted consequences of going too far and then having drug-induced long QT and subsequent drug-induced torsades, resulting in a fatal drug-induced sudden cardiac arrest. Number 3, here's the ventricular action potential, and we're going to look here at this part of it and have you tell me, what is the predominant inward currents that are open during this phase of the action potential? Are these sodium channels that must be open, potassium channels, calcium channels, or the funny current? So here we're looking and we're at phase 2. We talked about this plateau period is a balancing act, and the predominant inward current is calcium channels. The sodium channels have long ago been on and off. That was phase 0. And then we moved into the plateau being balanced by the inward calcium currents and the outward effluxing potassium currents. And for all the marbles as we finish, question number 4. What is the mechanism of action behind shaving-induced bradycardia? Shave, shave, shave. Or if we wanted to do a vagotonic maneuver to try to break SVT. You see, as you look through all those questions, we give you the first part, cranial nerve 10, that is the vagus nerve, is releasing the neurotransmitter acetylcholine. So we can go past that. But then does that acetylcholine, that ligand, bind to M2 or M3 muscarinic receptors? And then does it activate the G-alpha subunit or the G-beta gamma subunit as you're looking through them? And then as a result, is it blocking or turning on potassium channels? And as you work through that, as you go down the list, you see, bingo, the answer is number 4. Vagal nerve stimulation, releasing the neurotransmitter acetylcholine, binds to its muscarinic type 2 receptor, activates the G protein complex, and it's the G beta gamma portion that binds to and turns on that otherwise quiescent population of potassium channels, that of IKACH, to provide another hyperpolarizing, repolarizing force to pull the membrane potential more negative, to slow the next upstroke in the nodal system and thereby break the circuit if the AV node is involved. Well, I want to thank these entities for supporting our program. I've been delighted to get a chance to be here with you today, and I wish you all the best. I hope this lecture itself has helped us achieve the learning objectives as disclosed here, and best of wishes to you from the Mayo Clinic. Thanks a lot for spending the time with me today. Thank you very much.